Khan from Virginia Tech.
Hello everyone, I'm Jehandad Khan. I'm presenting my paper called Creating Custom Network Packet Processing Pipelines on HMC-Enabled FPGAs. This is co-authored with Professor Peter Thenis, who's my advisor back at Virginia Tech. So there are two primary words that are key in this talk, that is HMC and FPGAs. So HMC stands for Hybrid Memory Cube, and FPGA, as many of you already know, stands for Field Programmable Gate Arrays. So when it comes to packet processing in general, we believe back at the lab that FPGAs can be really the ideal coprocessor because they're highly parallel. In theory, every gate of an FPGA can operate in parallel. You can have arbitrary data paths that can both be arbitrary in terms of the paths that they take and their widths. Unlike traditional CPU, GPU architectures, there is no cache delay because if you do not foresee a temporal or a spatial locality for your data accesses, you do not need to instantiate a caching system or a memory hierarchy, which can be sometimes a big win for the system. And finally, they're very low power as compared to CPUs and GPUs. So in short, we love FPGAs. But then it's not all roses and candy. They sometimes can be really painful because of very long compile times, which can sometimes be in hours, and in some of the newer devices, even in days, if you have a 3D device or something. The design process is more like an ASIC and less a software design flow. So if you're familiar, they're usually very complicated, and verification of those designs is much harder. The expertise is relatively less abundant. You can find more GPU programmers and CPU programmers than you can typically FPGA programmers. It's not a secret, FPGAs are very expensive. And finally, the memory on chip of an FPGA is really limited as compared to other systems. So that sort of breaks our heart. Finally, but what we wanted to know was, if an FPGA is coupled with a hybrid memory cube, what kind of new applications or what kind of new scenarios would that bring in? Particularly in a packet processing sort of scenario, what is the maximum achievable throughput? What is the latency cost? Because a hybrid memory cube is a serial memory, it's not a parallel memory. And what are other trade-offs that we need to take care? So a hybrid memory cube is essentially a 3D IC with multiple layers of DDR3 chips stacked on top of each other, with the bottommost substrate layer being the memory controller itself, and then each of those memory chips are interconnected through silicon vias or TCVs. And because there are so many DDR3 chips packed so close to each other, that gives you a very high parallelism in terms that you can actually divide that memory cube into multiple vaults and then open and close different vaults at the same time, allowing a very high data throughput. Also, because all those chips are located in the same package, so you need very less number of pins to communicate between your host processor and the hybrid memory cube and the CPU or the host processor. So because of this, they are typically low power. They have very high raw random access bandwidth. So their raw random access bandwidth is equivalent or exceeds the serial memory access throughput of a GDDR5. That is a DDR3 being compared to a DDR5. Finally, because there's a memory controller sitting so close to the memory itself, you can do in-hardware atomic operations, which are not only limited to comparisons, but you can do binary operations like AND or an XOR. You can do increment and decrement, and any other operation if your bottom substrate itself is programmable. However, there's latency associated because you're talking to the memory using SERDES, which is serializer deserializers. That means that you have to go through that channel first, serialize your bit stream. It goes in a serial fashion to the memory itself. It is operated upon and then comes back. Also, the memory controller standard dictates that multiple memories can actually communicate with each other without the need of a special CPU or special logic. So that's part of the standard itself. The hybrid memory cube that we have is a 4 GB Micron HMC, which has four full width serial links. The particular platform that we have has two half-width links attached to a Kintex Ultrascale 060 device. This is a medium class device, sort of compares to an Intel FPGA ARIA 10. On the firmware side, we see 10 axis interfaces, each of which being about 128-bit in width. So in each memory access, you get to see 128 bits. So unlike a DDR3 memory, which has a 512-bit cache, and you get to pick or do whatever here, this is slightly smaller, but then there's an order of magnitude more parallelism that you can achieve. So if you just do random reads and writes, you can achieve a rate of 45 million lookups per second, and each lookup is 128 bits or 16 bytes. And then there's 6 of those devices located on an M700 backplane, and each of those devices can talk to each other using a PCI Gen 3x8 link, and the backplane itself can talk to the host, which is a Intel Xeon CPU or another CPU, using a 16-lane PCI Gen 3 link. So we have awesome hardware. I hope all of you agree. But then what do we do with this? So we decided that we want to convert P4 programs onto an FPGA. So a P4 program, by its very nature, is a data flow problem. There's no recursion, there's no loops. So that's why we believe that it is supremely easy or at least appears to be very easy to convert this into FPGA. And so what we start with is we do not touch the front end. We use the open source tool chain to convert the P4 program into a JSON representation. And then from that JSON representation, we extract the parser and then the table match action graph. We take each of those table match action graphs and convert them into Vivado HLS modules. Vivado HLS is Xilinx toolchain, which converts C++ programs into Verilog, and thereby and which can later on be compiled into an FPGA bit stream. So why did we choose HLS as our intermediate representation, if you will? Partly because we've already have some experience with using OpenFlow for packet processing, OpenCL for packet processing. Also, this helps us improve our turnaround time, because it's way easier to write code in C++ rather than in Verilog or VHDL, because the compiler ensures that if you write a C program, when it is compiled as Verilog, it would still obey the same semantics. So if you simulate it if you verify it in GDB or any other simulator, the Verilog would correspond to the same. Furthermore, and very importantly, it automatically pipelines the code. So you can take in a packet at each clock cycle and then emit one every clock cycle. The trade-off is relatively minimal. So the circuits that are generated from Vivado HLS are slightly larger, but given our huge devices, this is not as big of a problem. And also, this is slowly becoming a mature technology, and it also enables. So if you want to decide, I want to take a part of my logic that I do not wish to use Vivado HLS as my toolchain, you can just integrate Verilog into an existing Vivado HLS-based design. So the primary problem that we wanted the HLS to help us was the lookup problem. So any table that needs an off-chip lookup, we want to instantiate that as a Vivado HLS module that would interface with the hybrid memory cube. So because on-chip FPGA memory is very limited, so on the device we have, it's about between 25 and 30 megabits of SRAM, which is a very high performance memory, but we would rather use that as buffers and other precious resources rather than for our table scale. So we want to support multiple masks. We want to maximize our area and throughput trade-off, and also we want to exploit the hybrid memory cube bandwidth. So the way we do this is an incoming packet which is already parsed as a packet header vector. We feed the key fields into a bank of Bloom filters. Because we want to achieve a maximum throughput, we only have one shot at accessing the hybrid memory cube, and we want to make that shot count. So we feed that packet to a bank of Bloom filters, which tell us the probability if a particular packet would have a hit on the or would it be missed. So once that priority is resolved, we issue a request to the off-chip hybrid memory cube. The hybrid memory cube returns the result for that particular packet match, so whether it is matched or not, and if so, what is the action that should be operated upon, and then the returning result is used as an action operand, which modifies the data, and all of this logic is automatically generated based on the P4 program. But we also realize that not every packet needs an off-chip memory. For example, exact matches that are part of P4 programs need not be hosted on an off-chip memory. For that, we have a on-chip lookup, which is just an exact CRC32 based hash function. Some features of our toolchain is that for the parser we do expression balancing, we implement look-ahead implementation, and also we can have a variable flit. So if you want, you can have 128-bit incoming bit width for a particular packet, or you can have as high as 512-bit incoming packet bit width. Other than that, for any hardware implementation, you need to unroll your parser loops. We add our HMC interfaces. We merge the ingress and the egress into a single pipeline with the buffering in the middle. And also we generate the control plane API so that the host can actually insert rules from the other side. And finally, we add some measurement logic. So using this system, we generated we used simplerouter.p4 and then simplenat.p4 to do some measurements. And both of those systems we are able to achieve between 20 and 30 million packets per second. And this is just using a single hybrid memory cube channel in the case of the simple router, and 2 in the case of simple NAT, because for NAT there are 2 longest prefix match tables, both of which we implement on the off-chip memory. On a single FPGA, we are able to fit 3 of these pipelines, so the actual packet processing rate achieved is about 80 to 90 million packets per second, which easily surpasses any of those on a regular CPU. In the future, we hope that configurable memory cubes, which have an FPGA underneath the memory cube instead of a fixed controller, would enable many other interesting things, such as more complex atomic operations, etc. So based on those newer things, we hope that much more can be done with these interesting memory architectures. And that's all I have. Yes.
So I was a little confused. You mentioned that HMCs have some atomic actions and they support Boolean expressions within the memory controller. But are you exploiting those right now for table lookup, or are you just doing lookups?
We're not just doing lookups, but we can exploit them for for counters. So you can just issue an increment to a particular memory location and then just not worry about it. And in theory, you can have as many as you can fit in the memory, because otherwise you'd use an on-chip register for that, right? In the case of a CPU, you'd have to bring it from memory, and there'll be a cache miss and all those things. But in the case of a hybrid memory cube, all that overhead would not be associated with it, because it'll be more like fire and forget. You just issue the request and it's done.
Can you take a look at like 2 slides before where the performance is?
Yeah.
So 64K, 22.5, that's like a total of 20 G.
So that on the y-axis is the million packet per second, and on the x-axis is the packet length.
Right. So your packet length is
64 bytes. Yeah.
So it's slightly below 20 G.
Yeah.
Right.
Yeah.
So, but there are like single CPU systems that take 80 G per single box.
Yeah, but the CPU systems are limited by the amount of rules they can fit in their cache. So, for example, the DPDK results that they say it supports a 40 gigabit per second throughput, but then it's about 8,000 rules, right? So in this case, that is not a limitation. Also, this is for a single hybrid memory cube pipe, right? Whereas this FPGA only can fit 10 of those, whereas the HMC itself has about 40 of those. So because this is inherently a very parallel problem, you can easily parallelize those. So this is just one pipeline of the 10 that it can support. Okay, thank you.
I just did not follow that. What was the size of the group
Oh, so the question is, what is the size of Bloom filter and why do we need it in the first place? So then the latency between when I issue a memory access request and when I get the result is about 2 microseconds, 1500 nanoseconds, right? The 2 microseconds is the total latency of our pipeline, right? So if I have 32 masks of which I need to check which one of them would actually hit the rule for a longest prefix match or a tertiary match, right? So that means in theory, if I don't use a Bloom filter or anything else, I'd have to check all of them one by one. So I can do that all in parallel if I use 32 parallel channels, channel access to my Bloom filter, right? Or anything else. So to minimize that traffic between off-chip and on-chip, off-chip and the FPGA itself, we use an on-chip Bloom filter to tell us where the probability of hit actually exists.
So what is the false positive rate that
The false positive rate that I can recall is below 0.5%. So because our Bloom filter is implemented in on-chip RAM, and there's plenty of it because all our rules are moved off-chip, right? So that's why we can afford to have a larger Bloom filter.
Okay, last question.
Can we take that offline?
Sorry, but in the interest of time, cut it short. All right. So thank